Hi everyone. In this video I'm going to discuss autocorrelation and trends. Keep in mind that there's also a video on how to test for autocorrelation and trends using SSD for R in the R section. So I'm going to cover what an autocorrelation is, how can you assess the problem, we can also discuss trending data and why it all matters. Correlation is a measure of how predictable one variable is based on another. For example, education increases, we can predict how much income increases. So autocorrelation is a special type of correlation which comes up in time series research, and that's exactly what we're doing here when we're looking and analyzing a subject's behavior over time. So autocorrelation is a measure of how predictable future time points are from previous ones. You can't see autocorrelation by looking for trends in a graph, although highly trending data is more likely to be autocorrelated. In single subject research, you must look at autocorrelation of data in each phase before comparing phases. So your assigned readings will help you understand when autocorrelation is a problem and what all of those numbers mean. But it'll help certainly reinforce it for you. So if you think about autocorrelation, you have to consider that statistical tests rely on various assumptions, and when these assumptions are not met, incorrect conclusions about calculated values can be made, such as deciding that observed differences between two phases are significant statistically when they're not. That's called a type 1 error, as you recall from 6402, and we'll discuss this a little more later. And then you could also erroneously not detect the difference between phases when one does exist, and that's called a type 2 error. So an assumption in the analysis of data in single system research design is that each observation is independent from one another. This means that observations cannot be predicted from one another. When data lacks independence, they're considered correlated because data in a single system research is measured over time. There is a need to test for a special type of correlation, which is called serial dependency, and that is measured by a correlation known as autocorrelation. So when visual analysis is used, autocorrelation combined with variability in the baseline increases the likelihood of concluding that there's a difference when there isn't one between phases. So measuring autocorrelation is very important. So we're going to be using a command called the ABRF2, which will calculate the degree to which data is autocorrelated. So obviously the first thing when you try doing this yourself, and you could pause the video and use the get CSV to open the Jenny AB data set. And then the command to calculate autocorrelation would be the ABRF2, and we'll test it for the variable self-esteem, which we have as esteem and p-esteem, and here is the exact command you would use to assess for autocorrelation in the baseline. And the ABRF2 will be used in all phases, including the intervention phase. We would just swap the A out for a B. So go ahead, pause the video for a minute and take a look at what you see. So you notice in the the graph section, you have this graph, and notice that in the graph, how much of the data is not very close to the regression line. Also notice in the console that the RF2 is fairly low, and the significance is above 0.05. So autocorrelation doesn't seem to be a problem here. Let me bring up my my calculation here. So you can see here we have a few factors here. We have the TF2, which it relates to the significance level, but the actual quantitative measure of autocorrelation is the RF2, and here it's 0.387, which is fairly low. So there is some autocorrelation, but not enough for us to be concerned that it would have a detrimental impact. Also, it's not statistically significant, but the honest truth is I pretty much ignore significance. Now, the TF2 is used to calculate significance. So the important thing to key on here is the RF2. Now, if it's below 0.6, we're in safer ground. The lower, the better, obviously. But as in my view, almost all data that we use in single substrate design is going to be autocorrelated. The problem is it's hard to get significance unless there's a very high degree of autocorrelation to get significance, because the n's we use are very small. They range from 5 to 10 observations. So smaller degree, smaller size of n, less likely you're going to get significance. So so I just really look at the degree to which there is the autocorrelation. So here it's small enough for us not to be that concerned. Okay, I'm gonna minimize my my R and go on to the next slide. So now, so similar to what we saw in the baseline, autocorrelation doesn't seem to be a problem in the B phase either. That is in the intervention phase. Let me bring up my console again, and here I ran the command and I just swapped out the A with the B, and here it's higher. It's getting very close to what we would consider problematic, but it's 0.571. So there is definitely autocorrelation, but it's not as it's not at the 0.6 level. So we also can consider that although there is some autocorrelation, there are still statistical tests we can use to determine whether or not there are differences between the phases. All right, okay. But again, key on that RF2. That's the most important thing. Let me minimize my console here. Okay. So let's but what if autocorrelation were an issue? You could attempt to transform your data. However, I think for the purposes of this class, we will simply make note of it and not try to address the problem through transformation. It might be some of you would like to try it, and I'd be glad to help you along in doing that to see what that's like. But I'm not going to require it. So you would address issues of autocorrelation in any phase by using alternative statistical methods to compare the phases. So just to talk about that again, there's something called a CDC, which would allow you to compare phases if you're at autocorrelation, and we'll talk about that when we get into analyzing intervention data. For now, it's just important that you note if you have an autocorrelation or not that is problematic. Again, 0.57 is autocorrelation. There is some autocorrelation, and it can impact type 1 error or type 2 error. That is, it could have some impact, but it's not as worrisome if it was 0.6 or above. Okay, so we'll use that as our cutoff. Okay, remember that number. An autocorrelation of 0.6, we'll consider that we need to use alternative methods. So for this paper that you're writing on the baseline, just note if your data is autocorrelated or not. Okay, now recall that we talked about trending data. Well, I guess we haven't really talked about it, but trending data, we can assess the degree of trend by looking at ordinary least squares on the regression line. So we could take a closer look at data points using a regression line. The more the data trends, like autocorrelation, you need to assess for a trend in each phase of your data, and you could consult your assigned readings for more on trending data. There's also an example in the section on SSD for R in the R section. So you can do an exercise yourself using the GenAB CSV dataset, and you could use the regress command, and you could do it with the calling out behavior. And we have it's very simple. It's just regress call out comma p call out, and A if you're doing the baseline, and when you get to the intervention it would be B. Pause it for a couple of seconds and try running that. So here's what it looks like. So notice in A that the data points are very close to the blue dotted regression line, and notice that the T is 0.05. That means that the trend we see is significant or statistically meaningful, whatever terms you want to use. And the same thing here for B, that there seems to be a trend in both the A and B phases. So let's take a look at that more closely. I'll bring up my console again. So here's A, right? So here's the command regress call out p call out, and we have the coefficients. We have the intercept and x1. Now x1 is what's known as the slope, and so that's the average amount, if you think about it, of change from one observation to the next. So it's going up on an average of one call out incident a day. So you could see the line here, and you can see how close the trend is here. So and that value is significant at the 0.05 level. We have 3 stars next to it. Actually, it's below 0.05. It's below 0.0. So we have, not, as I said, we have a statistical significant trend. And so trending would be a problem here in the A phase. Let's take a look at the next phase. I'm going to get the graph here, B. I just clicked that arrow because I had it saved there. And you can see that the trend was totally reversed, which is a good thing in terms of an outcome. But again, we have a trend here. So if we calculated the means for each phase, then it would seem the means would be very similar to each other and would look like there was no real change in the behavior because the differences would be zero. So here it's going down at a rate of 0.6, right? So it's changing downward, trending downward a little more than half a call-out episode a day. So it's going down quickly. Here it was going up, obviously switch back to A, it was going up faster, which means it would just keep going up and up. I mean, that's a strong trend going up at almost a point, and then going down a little over half a point. So like every 2 days it went down a point. That is, went down one call out episode. So look at that slope and think about it in terms of the type of measurement you're doing. So here we're thinking of it as units of 1, right? Because it's 0, 1, 2, 3, 4, right? So in this case, it's going up almost a whole unit per day. That's a lot. So if you did nothing, it would be really problematic for this client. But there is a trend, and again, trends will have some impact on the type of analysis you can do. So for now, for the baseline, just indicate whether or not there's a trend. So basically, why does it all matter? Well, statistical tests comparing phases assume that data are independent from one another. If you see autocorrelation or a trend in any phase, you can assume that the data are independent if you don't see one. Therefore, different statistical tests are needed to compare phases if there is an autocorrelation. And we'll discuss the statistical tests in another video. Stay tuned. That's later in the course. Just get through your baseline paper, noting whether or not you have autocorrelation or a trend in your data. Both very important to keep in mind. By the way, even studies have found that if you have autocorrelation, even just looking at it visually makes it difficult for people to determine, and they determine incorrectly, if there's a difference being made as a result of the intervention. So regardless of even statistical tests, autocorrelation can affect how we visually interpret what we see in our graphs. So it's very important to measure whether we have autocorrelation or whether we have a trend. And again, I'll say it again, all you have to do for the baseline paper is to just note the degree of autocorrelation you have, so we know if it's autocorrelated or not. And 2, for trending, just note whether or not you think there's a trend in your data. And to show the analysis and interpret it the way I did in this video, and there's another video that you can look at that keys on doing it just for the baseline phase. Thank you.